Okay, guys, this particular video goes on in talking about exponential functions. So we're talking about e to the x still. And if you recall, what we talked about before was the fact that the ln function, the natural log function, and the e function are inverses of each other. So some unique things happen when we put these two things together. So for example, if we have got the natural log of e to the x, then this can be simplified as being equal to x. And then if we've got e to the natural log of x, we're going to get x for an answer as well. So these are two properties that you need to be familiar with. This actually doesn't even come from calculus. This comes from second year algebra. So make sure you're familiar with those properties and you understand the relationship of the natural exponential function itself. Remember, it's y equals e to the x. If we were to take the natural log of both of those sides, we would get down to the derivative of those, which we're going to do in just a second. Okay, so I'm not going to spend any time here really talking about basic operations and properties with the natural log because they all have to do with exponents. Remember that when you multiply like bases, you're going to add exponents. When you divide like bases, you subtract, etc. So everything in association with this e to the x is still going to work that way as in terms of functions with exponents in them. Okay, so let's get on to the stuff that's really important, and that is the derivatives. So how do you find the derivative of an exponential function? These are real easy. So the derivative with respect to x of e to the x is, you're going to like it. I'm not going to tell you what it is right now. I want you to think about it for a second. What is this thing, right? Isn't e equal to like 2 point something, something, something? So if it is a straight up numerical value, then any value that I put in there for x is just going to be itself. So the derivative of e to the x is just e to the x. Super easy, right? So keeping in mind then that if we expand on that a little bit, if we've got, let's say, the derivative of something that is not just e to the x, but let's say it's e to the 2x, then not only am I going to say the derivative is the same thing that I started with, e to the 2x, but I'm also going to have to then take the derivative of whatever the exponent is, okay? So it's kind of like, again, that chain rule type concept where you not only take the derivative of what's outside, but then you also have to think what is the derivative of what is inside as well. So let's do another one like that. Let's do it like this. Let's go with e, the derivative with respect to x, e to the 2x minus 1. So my derivative, first of all, I can just think about this as being, oh, well, it's the same thing, e to the 2x minus 1. But then what's the derivative of this? So I want to take it times the derivative of 2x minus 1. When I derive this, I'm left with a 2. So it's 2 times e to the 2x minus 1. All right? If you have something different like this, the derivative with respect to x of x squared e to the x, what you need to notice is there's something else going on here. You've got a product rule that you have to do here. Okay, so this is a product rule. So you take derivative of the first times the second. Let's just work that real quick. Derivative of the first term or second term, it doesn't matter which one of these you do in order. So derivative of the first term would be a 2x times your second term, which is e to the x, plus the derivative of your second term times your first. Well, that's just going to be the exact same thing. So my answer is basically just this. Now I can simplify that a little bit if I wanted to. For example, they both have e to the x, so I could pull that out. That leaves me with 2x plus x squared. And then I could also pull out an x. So x e to the x, that would leave me 2 plus x on the inside. Okay? So it's not so much that the exponential function is going to be a problem in and of itself when you're deriving it. It's that you're going to have to go back and think about doing that in association with things like the product rule or the quotient rule. Okay? So take your time, do things in steps. Don't rush yourself and don't expect too much of yourself either. All right. The second piece to this then would be the integrals of the exponential function. So the integral of e to the x dx, I bet you can figure this one out real easy, right? If the derivative is itself and the integral is the antiderivative, then if I take it and do the antiderivative, I end up back where I started. But in this particular case, it's still the same thing. So it's e to the x. And if it's an indefinite integral, again, we add the constant to it. So e to the x plus c. So let's do an example on this one. Let's say that we've got the integral of e to the 3x plus 1 dx. So if I want to integrate this, what I want to do is I want to think about this in terms of what might make it most like what I know how to do. Just like we did with those natural logs, the u sub feature comes in really important here. Okay? So if this were just e to the x, I'd know how to integrate it. It'd be super easy. It's not. It's this. But how can I make it into just e to the something? Well, I can make u equal to 3x plus 1. So if I do u equals 3x plus 1, do a u sub here. Du equals 3 dx. So du over 3 equals dx. I've got e to the u times du over 3. Now I've got this constant I can pull out. So 1/3 the integral of e to the u du. That's easy. I can do that one. That's going to be 1/3 e to the u plus c. Now I can just go back and plug back in for my u. So I've got 1/3 e to the, and then u was originally 3x plus 1. So 3x plus 1 plus c. Okay, so you're combining u subs with other factors of working with that exponential function. Let's look at one or two more here, and that finishes out the section because that's all that section is about, is the exponential function. So let's look at one more indefinite integral. Let's do the integral of e to the 1 over x squared dx, and talk about how you would integrate this one. Okay? What I would recommend that you do for this one is pull that x squared and treat it as its own thing. In other words, kind of separate this out a little bit. If I know that the integral of e to the x is e to the x, then I want to, again, make this thing look like I want it to look. So let's do it like this. E to the 1 over x times 1 over x squared dx. So now I'm getting closer to looking like I need it to look. All right. Now, what I could do is I can again do a u sub. Now here's the interesting thing. My u sub right here, I want to make it equal to this exponent, right? So this then is going to be e to the u. U equals 1 over x. So if I derive u and I derive 1 over x, think again about this being x to the negative 1. So I'd have negative x to the negative 2 dx. Okay? So divide this. It disappears. And I'm left with then times negative 1 over x squared. So when we do this, then again, we're going to substitute for dx. Dx, we're substituting in du, negative x to the minus 2. Well, negative x to the minus 2, that means this should be on top, or I could move that on top. In effect, here's what's happening. Look, if I end up with this, those two cancel each other out. The pluses cancel each other out. Now I'm left with the integral of e to the u du. Super easy. So if I translate that back over, then put my substitution back in. U was 1 over x. So I put my 1 over x back in, and then plus c. I think actually I left I had a minus sign left off there, but okay. So when we then look at it as a closed interval, then what you're going to do is the same process, but just at the end, then you're going to do it in terms of the actual bounds. So if I've got the integral of 0 to 1 of e to the negative x dx, then the first thing I want to do is derive x. So I find my derivative or my integral by taking the integral of this, which I know is just going to be the same thing again, but then the derivative or antiderivative now of that exponent. I'm going to do this the shortcut way because I've now worked this enough in my head that I know that if I take u equal to minus x, the derivative is going to be du equals negative dx. So du over a negative 1, which is just going to give me a negative e to the minus x. Okay, so put my bounds on, and then you just plug your value in and substitute, and solve it. So negative e to the negative x. So we start with your b bound minus e to the negative your a bound. Now what's nice about this is anything to the 0 power is 1. Okay? And then you've got here your minus e to the negative 1. Well, that means a negative 1 over e. And so you are left with a negative 1 minus 1 over e. Okay? All right. So that's it for e's. Just double check your examples and stuff in section 4 and do some practice with those.